We'll show you how to find the circulation and flux using the differential form of circulation and flux. So by definition, the circulation is the line integral of f dotted with the unit tangent vector ds. We saw other versions of this in a different video. However, in differential form, it looks like this. We want to do f dx plus g dy, where the field is given by the functions f and g, typically functions of t. So let's do that. Here is the function that represents our curve. Here's our field. And so what we need to do is to take the field and use f for the first component, g for the second component. So when we have the field f comma g, that's what f and g are. However, we're going to get the values of y and x from the curve. So the first component would be x and the second component would be y. So here is what our integral looks like. We're going to have f, which is negative y, which y is 4 sine t. So that would come out to be negative 4 sine t. Now, if we've got x equals 4 cosine t, then dx would be the derivative of 4 cosine t, which would be a negative 4 sine t dt. And the function g, which is x, but x is the 4 cosine t. And the dy means the derivative of the y component of the curve. The y component is 4 sine t. The dy then would be the derivative of 4 sine t, which would be 4 cosine t dt. Now, as you see, we can take the dt's totally out of each of these, and we're left with a negative 4 sine t times negative 4 sine t, which is a positive 16 sine squared t. 4 cosine t times 4 cosine t would be a positive 16 cosine squared t. Now, the values that we're integrating over are given right here. So we're going from pi over 6 to 2 pi. We can simplify this further by factoring out the 16, leaving us with sine squared plus cosine squared, which equals 1. So this is the integral from pi over 6 to 2 pi of just 16, which is easy enough to do by hand. This comes out to be 88 pi over 3. Now, in looking at the field and the curve, we notice that this is a circle with a radius of 4, which begins out here at 4, 0, and goes in the counterclockwise direction. So as you see, we're pretty much following the field. In other words, we expect a rather large value for circulation. And indeed, we have a rather large value for circulation. The formula for flux, by definition, is the line integral of F dotted with capital N, the unit normal vector, with respect to arc length. However, in differential form, this looks like this. We have the integral of F dy minus g dx, where the vector field is where the F and the G come from. So it's the same F and G I just got through working with. Here is the little f and the little g. And so the formula for flux would look like this. We would have F, which is negative y, and y is 4 sine t. Times dy. Now, if y is 4 sine t, dy would be 4 cosine t dt. Minus, now g is x, and x is 4 cosine t. And then dx, here's the x component, whose derivative is negative 4 sine t dt. And as before, the dt's will factor out, and we can combine some of the other stuff together. And as before, this is going from power 6 to 2 pi. So negative 4 sine t, 4 cosine t would be a negative 16 sine t cosine t. The negative 4 cosine t times negative 4 sine t would be a positive 16 sine t cosine t. Well, we really don't need to go any further because negative 16 sine t cosine t plus 16 sine t cosine t is 0. And it doesn't really matter where you're going from and to, or what you're integrating with respect to, that's a 0. And likewise, I suggest that that looks plausible in light of the vector field and the curve. If we're going around the circle, notice we do not have any normal vectors. All of the vectors are going along with our circle. So there's no flux.